Hi everyone, so today we are going to be covering section 8.2 from the textbook, which is integration by parts. So integration by parts is going to be a new integration technique that we're going to be able to utilize in order to take integrals of certain functions. So kind of as a nice motivating example for this, let's think about two different possible integrals we might want to be solving. The first one is the integral of e to the x dx, and the second one is the integral of x e to the x dx. Okay. So this first integral is relatively easy, right? We know that this is going to be e to the x plus c. However, just by this addition of multiplying x in the front here, we now no longer know how to solve this integral. None of the techniques that we currently have work for solving this. If we try to do, say, u substitution, a choice might be to set u equal to x, but then we've just kind of switched around the variables. We still would have the integral of u e to the u du. So nothing would change with that choice of u, and none other choices of u work as well. So this is why we need to introduce integration by parts. It allows us to be able to solve a much wider range of integrals. So integration by parts is the opposite of the product rule. It's the integral version of the product rule. So you will most often see it used when you have the product of two functions. So in this case, it's x times e to the x. So what we're going to do right now is I will write down the formula that we're going to use for integration of parts. Then we'll go through an example with this x e to the x. And then we'll talk about when you want to be using this, some of the choices I made throughout the process, and then we'll go through a few more examples as well of different times you might be able to use this, in different cases you will be able to use this. So if we have u and v are functions, integration by parts is the formula that the integral of u times the derivative of v is equal to u times v minus v times du. Okay. So we are multiplying two functions together, and after we do this, we get out some functions multiplied together minus a new integral. And this new integral is hopefully one that's going to be easier to solve. So for the first problem, I claim that if we set u equal to x and dv equal to e to the x dx, this is going to work for this problem. Okay. So if we look at the formula we have on the right-hand side here, we have the u part. However, we don't know what v is. We will integrate dv to get v. And similarly, we will need to take a derivative of u to figure out what du is. So starting with the derivative, if we take the derivative of u, we're going to get that du is equal to dx derivative. Similarly, if we would like to get v from dv, we are going to take an integral. Well, the integral of e to the x is still e to the x, so v equals e to the x, and this is solved with an integral. Okay, so plugging things into our formula, we have it as desired, right? U dv is the integral of x e to the x dx, and we have that this is equal to u times v, or x times e to the x, minus integral of v du. V we have from above is e to the x, and du is d to the, or dx. So e to the x dx. And this is great, right? This is an integral that is much easier to solve. It's actually what we were talking about before, where we now have this as x times e to the x minus e to the x plus c. Never forget your plus c's with these indefinite integrals. It's very easy to make that mistake. Okay. So I did make a choice when I was doing this problem, and that choice was I picked that u as x instead of dv as x. The reason I did this is that we are taking our derivatives of x. And so after we take a derivative of x, it's going to turn into a dx, which generally makes the problem a lot easier because now you're multiplying by a constant instead of by a function x. And so in general, a good choice for u is going to be polynomials. We will talk about one example for the very last example actually in this lecture, where this is not going to be the case. But in general, that's a pretty good choice because we'll start taking derivatives and derivatives and derivatives, and eventually the polynomial will go away and we'll be left with a constant, which is much easier to deal with integrals of. The second good rule of thumb for these is we want dv easy to integrate. Right, so I don't want to pick, in this example, dv to be all of x times e to the x because we don't know what this integral is already. So we want dv to be something that is easy to find the integral of. Okay, let's go through another example of this as well, and we'll, just go through another example. Example is x sine of x dx. This is an integration by parts question because we are multiplying two functions together and a u substitution doesn't seem to work for this problem. That's a general good takeaway from this, is if you are multiplying and you've tried u substitution and it's not working, you probably want to do integral by parts. Okay. So we need to know what u is, and we need to know what dv is. Well, using this idea from above, good choice for u is polynomials. We're going to set u as x and dv as sine of x. So, as you recall, we have our formula as u dv equals uv minus the integral of v du. So there are these two extra pieces we need to know. We need to know v, which we get from integrating sine of x. So the integral of sine of x dx is going to be a negative cosine of x. And finally, we also need to know what du is. In this case, very simple, same as the last problem, du is going to be dx. Okay. And we can now plug everything in. So the left-hand side right here matches up. We have u times dv is x sine of x dx, which is what we want to take the integral of. So integral of x sine of x dx is equal to u times v, or negative cosine of x, cosine of x times x minus the integral of v. We have a minus in this cosine here, which will make this positive, so positive cosine of x times du, or times dx. Okay, this is great. We know how to take the integral of cosine. Integral of cosine will be sine, and so we have negative x times cosine of x plus sine of x plus c. So the third example that we will be going through for this problem is a repeated use of the integration by parts technique. So example 3, repeated use. And I kind of alluded to this earlier when I was talking about picking u as a polynomial. So the problem we are going to be dealing with right here is x squared e to the x dx. Now, the first time we're going to do integration by parts, we will have a du, which was going to be a 2x in this case. And so what that means is that we're going to have to use integration by parts again in order to get the integral we have at the end. Okay. So let me go through the process of doing this. So good choice for u is going to be our polynomial, or x squared, and v is going to be e to the x, dv is going to be e to the x dx. All right, we are taking derivatives of u to get du, so du is 2x dx, just by taking a derivative of x squared, and we take integrals of dv to get v, which in this case, integral of e to the x is still e to the x, so v is e to the x. Right, our formula for this is going to be, as we recall, u dv equals u times v minus integral of v du. So plugging everything in, we get that u times v is x squared e to the x, and then minus 2 integral of x e to the x dx. So the 2 came from the 2x. So this integral here should look like an integration by parts question. It's actually the very first question that we did, right? We took this integral in order to solve for it. So in this problem, what we're going to do is we are going to use integration by parts again on the integral left over here in order to solve the problem. So we take all of this and we are going to solve it by integration by parts. Okay, so we need another u and another dv. Well, in this case, we can set u equal to x, dv equal to e to the x. Derivative of u is the derivative of x, and the integral of e to the x dx is e to the x. So we get that this yellow highlighted part, -2 integral of x e to the x dx, is equal to -2 times u times v. So our new u and our new v are going to give me x e to the x. And finally, I have the integral of v times du, or e to the x dx. And this is great, right? We've now reached a point where the integral we have in our equation is something we are able to solve. So this is -2 x e to the x, and the integral of e to the x is e to the x, so minus e to the x. So combining this with this x squared e to the x we had before, we get that our integral of x squared e to the x dx, and I did forget a plus c there, is equal to x squared e to the x minus 2x e to the x minus e to the x plus c. So a lot of times when you're doing these problems, especially if you have a polynomial that you're looking at as your u, you will have to do a repeated integration by parts in order to get that polynomial down to a constant so that your final integral is easier to deal with. Okay. So the fourth example, example 4, is one where it is not immediately clear that we are going to be able to use integration by parts on it. We would like to evaluate the integral of natural log of x dx. Okay. So this is a technique that is not extremely common. However, you are expected to know how to do it for problems very similar to this one. So if you are dealing with integrals of, say, natural log of 3x or something like that. But the idea here is that we can think of natural log of x as this is actually equal to natural log of x times 1 dx. And what we then choose, as we choose our u to be natural log of x, and we choose our dv to be just equal to dx. The reason we choose it this way is if we were to choose our dv as natural log of x, well, this would kind of defeat the purpose because we would need to take an integral of natural log of x, and that's what we're trying to figure out. So we'll pick our u as natural log of x. Okay. The derivative of u, du, is 1 over x, and the integral of dx is v equals x. Throw dx on there. Okay. So now we can take all of this information, we can plug it into our integration by parts formula, and we can get out our answer. So our answer is going to be this natural log of x dx is equal to u times v, x log x, minus the integral of v du, so x times 1 over x dx. Well, x times 1 over x is 1, so we're taking the integral of 1 now, which is just x. So this is x natural log of x minus x plus c. So when you are doing integrals, and you might run into something like natural log of x, where it's not multiplication, you can't really do a u substitution on it. It doesn't fall into any of the other categories that we've talked about. This is a good kind of resort to try to solve these problems. It works particularly well with logarithms as our thing that we are integrating. Okay. The fifth thing we are going to talk about, example 5, is going to be definite integrals. Right? Definite integrals are where we have bounds on our integrals. So the formula is kind of what you think it would be if you were to think about it, but just to write this down very formally, the integral from a to b of u dv is equal to uv evaluated from a to b. Right? This is the same notation that we use when we do integrals, where we're going to plug in b for u times v, the variable in there, and then we will subtract out what happens when we plug in a. So this is the same thing that happens when we take integrals and we get our antiderivatives. Then we subtract the integral with zero bound change, so still the integral from a to b of v du. Okay. So just going over a quick example of this, we take the integral from 0 to pi over 2 of x cosine x dx. Now, for this problem, we can pick our u as x. Makes sense, it's a polynomial. It will become 1 after we take a derivative, so it's a very good choice. And we will pick dv as our cosine of x dx. So u is x. That means that the derivative of u is dx. And we also have that dv is cosine x dx. The integral of cosine of x is the sine of x, positive sine of x. So v is sine of x. So evaluating this integral from 0 to pi over 2 of x cosine of x dx is equal to, looking above, we see that this is u times v evaluated from a to b. So x sine of x evaluated from 0 to pi over 2. Right, so we're going to plug in pi over 2 for x, and then subtract out the result we get when we plug in 0, minus the integral from 0 to pi over 2 of v, so sine of x, times dx, or du, which is dx. So sine of x dx. Great. So taking these and figuring out what they're equal to, we have that this is pi over 2 times sine pi over 2 minus 0 times sine of 0, and then all subtracted from the integral of sine of x, so this is going to be now cosine of x evaluated from 0 to pi over 2. Okay, if you remember back to your unit circle, sine of 0 is 0, and sine of pi over 2 is pi over 2, so this will become 0, multiplying 0 by 0. And this first part, this pi over 2 times sine of pi over 2, just becomes pi over 2. So we have this pi over 2 minus cosine pi over 2 minus cosine of 0. Okay. Cosine of pi over 2 is 0, so this is 0, and cosine of 0 is 1. So we have minus a negative 1, which becomes pi over 2 plus 1. So the last thing that we are going to be talking about today in this integration by parts section is going to be another variation of using repeated integration by parts. So the example that we are going to go through for this is the integral of e to the 2x sine of x dx. Okay, so if we think about going through this problem using integration by parts, if we pick, say, u to be sine of x, what's going to happen is we'll get an integral with an e to the 2x and a cosine of x in it, and then we'll need to do this again because this is still not an integral that we're going to be able to solve. So what's going to happen, because this sine of x is going to repeat as we keep taking derivatives and keep taking derivatives, doing it twice, we will get back to a sine x. What we will do for this problem is we will use integration by parts twice. We will then get this integral of e to the 2x sine of x equals a bunch of functions, and then plus a constant times e to the 2x sine of x dx, and then we can isolate this new integral and get that this is equal to the functions. So I'm going to go through how we do this for the problem. So in general, for these problems where we do this type of repeated, where we're going to come back to the same integral, it doesn't matter which you pick your u as and which you pick your dv as. In general, though, it's a good idea, I think personally, to pick your u's as your trig functions. These will be the ones that are repeating. So if we set u equal to sine of x, dv equal to e to the 2x dx, taking a derivative of sine of x leaves us with cosine of x du, cosine of x dx, and an integral of e to the 2x is 1/2 e to the 2x. Okay, so plugging this back into our integration by parts formula, we get that the integral of e to the 2x sine of x dx is equal to u times v, or 1/2 e to the 2x sine of x minus the integral of v times du. So minus 1/2 integral of e to the 2x cosine of x dx. So the next step that we're going to do for this problem is we are going to take this integral here, and then we are going to perform another integration by parts on this. After we do this, right, as I was saying before, we will be left with an integral of e to the 2x sine of x, and so we can isolate for this in order to solve. So dealing with this highlighted part right here, if we pick now, very similar to before, u is going to be now cosine of x instead of sine of x, dv as still e to the 2x. We get that du, the derivative of cosine of x, is negative sine x dx. And again, the integral of e to the 2x dx is v equals 1/2 e to the 2x. So solving this, we have that the integral of e to the 2x cosine of x dx is equal to u times v, so 1/2 cosine e to the 2x, cosine x e to the 2x, and then minus a negative sine of x e to the 2x, negative 1/2, so positive 1/2 e to the 2x sine of x dx. We can now plug this back in for the highlighted part to get that the integral of e to the 2x sine of x dx is 1/2 e to the 2x sine of x minus 1/2 times all of the things we said the highlighted parts were. So minus 1/2 cosine x e to the 2x plus 1/2 integral of e to the 2x sine of x dx. Now this is a great place to be in because we now have an e to the 2x sine of x and an e to the 2x sine of x right there. And so we can move this right-hand side equation over to the left-hand side and then divide by the constant in order to get that this integral is just equal to this linear combination of the functions. So in particular, I am going to add a 1/4 e to the 2x sine of x dx on both sides because that will get rid of this minus 1/4. So this turns out to be 5/4 integral e to the 2x sine of x dx is 1/2 e to the 2x sine of x. And I should probably have a plus c. Never forget your plus c's. Plus c somewhere in there. Minus 1/4 cosine x e to the 2x plus c. We can then now multiply both sides by 4/5 to get rid of the constant in front of the integrand, and we get that this e to the 2x sine of x dx is equal to 4/5 1/2 e to the 2x sine of x minus 1/4 cosine x e to the 2x plus c. Just as a side note, right, we can pull out this plus c right here because this c just signifies that we can add some constant on at the end. And so if we multiply 4/5 by constant, it's still just going to be some constant. So it's okay to just have the plus c sitting out at the end. Okay. And this is our final answer. So we have that the integral of e to the 2x sine of x is all of this right here. So the best way to recognize these integration by parts type problems for this one is if we are multiplying two functions together, like most of these integration by parts, and u substitution doesn't work, and we have a either sine of x or a cosine of x. So the reason we want to deal with both of these functions is that we will get this repeating action where when we take derivatives of the sine of x, we will eventually get back to some constant times sine of x, and we can isolate for the equation. All right. Thank you all for listening.